Hello everyone, let's take a look at our next problem. Find the absolute maximum and minimum values of f on the set D, where f of x and y is equal to 4xy squared minus x squared y squared minus xy cubed, and D is the closed triangular region in the xy plane with vertices 0, 0, 0, 6, and 6, 0. Okay, so we essentially have a two-dimensional optimization that we have to do on a compact set. So the first things that are coming to mind here are taking partial derivatives and setting them equal to 0, but that's of course only a necessary condition for finding minima and maxima. We'd have to verify that any points we get like that are indeed a maximum or minimum. But then also we have to look at the boundary of this region, which is a triangle. So what I'm thinking to do on the boundary is basically restrict the function to each of these line segments and think of it as a function of one variable on that line segment, and then just use standard calculus to find minima and maxima on the line segments, including the endpoints, and compare any minimum and maximum value on those line segments with any minimum or maximum values that I find in the interior. So let me write out the details of the problem here, and then we'll start doing some computations. Okay, so I'm going to start by writing out the partial derivatives of f with respect to x and y. So let's first solve for our critical points, so the points where the values of x and y, where both of these partial derivatives are equal to 0. Okay, so both of these partial derivatives are 0 along the horizontal axis when y is equal to 0 here. Also have that if I can find an intersection between these two lines, or the both of these equations define a line in the plane. If they intersect within the region D, within this triangle, then that'll give us another candidate for minima and maxima. But once we go through all this and find all possible points, I'm still going to look at the boundary and see what happens. Okay. So this point here at 1, 2 gives us a critical point where both partial derivatives are equal to 0. I'm forgetting now exactly what the test is to see whether this thing is actually gives a minimum or maximum. What is the two-dimensional equivalent of the second derivative test? Do I just take the matrix of second derivatives and take it's a determinant or something like that, isn't it? I think that's correct. I'm going to continue assuming that my memory is correct here, and then but I'll look up that result later. Okay, so let's compute second derivatives. And the point I'm concerned with here is 1, 2. So I'm just going to evaluate each of these when x is equal to 1 and y is equal to 2. Okay, so this determinant is greater than 0, which means that we do have a minimum or maximum, and you'll see that both of the pure second derivatives are negative, meaning that we have a maximum of our function at this point. So let's figure out what the value of the function is there. Okay, so the value of our function is 4 at this point. And that's going to be the only interior minimum or maximum. So what I want to do now is I want to look along the 3 edges of the triangle and find both the minimum and maximum along those points. Yeah, okay, so x equals 0, this gives, so f of 0 comma y is equal to, well, it's equal to 0 everywhere. Okay, when y is equal to 0, f of x 0, I believe, also gives us 0 everywhere. Yeah, and now what I want is the line that goes through 6, 0, and 0, 6. So I want to think of this, see what kind of function we have there. Okay. I'm not going to expand this. I'm just going to differentiate this. Differentiate this with respect to x directly using chain rule, product rule, and all that. Let's call this function g of x. So this is the value of the function along the slanted diagonal part of the triangle, as it depends on the x coordinate. So I'm going to set this equal to 0 and solve for x, but I'm going to allow myself to cancel off a 6 minus x everywhere. I know that when x is equal to 6, y is equal to 0, and I know the value of the function there already. It's equal to 0. All right, and so this function, or our function along the diagonal line segment, has a critical point when x is equal to 2. So x is equal to 2 implies that y is equal to 4. Do we have a minimum or a maximum value there? Well, let's just substitute in, see what the value of a function is. Okay, so the value of the function at that point is equal to negative 64, which is clearly not going to be a maximum compared to what we had in the other one. This will be the minimum of our function. I'm pretty sure that this is all of the possible maximum and minimum values of f. The gradient, if we go back to our little diagram here, the gradient was equal to 0 along here. So that kind of means every point along this, along the horizontal axis here, is a candidate for an optimal. But this point, and also, I suppose, the other point that we picked out for here is that one. So this is 2, 4, and this is 1, 2. We have the value of the function there. I forget what it is, but 4. And the value of the function at this point here is negative 64. The function is 0 along both of these, both of those horizontal and vertical lines, so we know that's not going to compete for the minimum or maximum. This is the only interior critical point, and then along all of the boundaries, that is the minimum. So that's going to be my answer, right? These are the locations of the minimum and maximum. The actual values I've computed below, but they're easy to find by substituting. If I have any other additional comments or I find a silly mistake here, I'll write it up in the description. Otherwise, thanks for watching.